welcome back on my channel. Today we'll try to create Python code, but let's think about it as a case study. So in this video, first of all, we're starting with problem, what we need to solve. Then we start with our approach. Thus then we will see which Python code we create to solve this one. So let's start with our problem and how we can solve it. So the problem is we are trying to optimizing warehouse storage using Python. Our statement is the warehouse manager is facing inefficiency in storage location. Large items are taking up excessive space and retrieval times are increasing. The goal is to optimize warehouse space allocation by implementing an efficient bin packing algorithm. And our solution, and so which we try to implement now, is we'll use the first fit decreasing algorithm, a well-known heuristic for the bin packing problems. This approach sorts items in descending order and places each item in the first bin that has enough space. And let's jump to the code, and we're starting with first one, so import necessary, in this case just import random. Then we'll create function. First fit decreasing with two things that we need to have, item size and bin capacity. What we're doing here, we're implementing first fit decreasing algorithm for warehouse storage optimization. Param item size list of item size to be stored. Param bin capacity is maximum capacity for each storage unit. What we return is number of bins used in item distribution. Step number 1 is to sort items in descending order. So in this case, sort items is equal to sorted, item size reverse true. List of bins, each bin is a list of items it contains. Step number 2 is place each item in the first bin that has no space. So for each item in the sorted item, place is equal to false. Then for bin in bins, if sum of bins plus item is smaller than bin capacity, bin append item, place is true, then we are break. If no bin could accommodate the item, we create a new bin. So if not placed, bins append item. Then we return the list of bins and bins. Let's now jump to simulate warehouse items size in cubic meters. For this case, we put random seed for reproducibility, then 20 items which size between 5 and 20 cubic meters, and each storage unit has capacity of 50 cubic meters. Okay, so bin capacity equal to 50. Then let's run the optimization algorithm. So num-bins bin distribution is equal to our function. So fit first decreasing, then we put items which we create, and bin capacity which is using here. Then let's go and display the results. So we're printing total storage units requires the number of bins, and for E, bins in enumerate, bin distribution, let's print storage unit and total number of cubic meters. So we can see it here like total storage units required 5, storage unit 1 and see the numbers, so unit 2 the same, 3, 4 and 5 the same. And why we're choosing this approach, the FFD algorithms provide a near optimal solution with all analog complexity, making it practical for warehouse use. Scalability can handle large dataset and dynamics item size. Implementation simplicity is easy and we plan to modify for different warehouse constraints. Alternative approach you can choose best fit algorithms, place item on the tightest fitting bin, slower but sometimes more space efficiently, and genetic algorithms, more composition and fixed but useful for complex constraints. And this approach strikes a balance between efficiency and complexity. Okay, and that should be it for this video. Thank you for watching.